looking at section 4.0. This is this whole chapter is just 4.0, and it is looking at determinants. And the way I'd like to start out is just kind of thinking about this name determinant. It determines something, and to show that we have things like this that we use in other ways. So let's think about we know something called a discriminant. So suppose I want to solve a quadratic equation, ax squared plus bx plus c equals 0. Well, in order to solve this, I'm not going to go through the whole derivation, but I would divide by a, c over a equals 0. Then I would complete the square with this part, and keep going, and dot dot dot. I would get to x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And then that part inside the square root is the discriminant. And that's also a good name, discriminant, because it discriminates between three types of solutions. So, if b squared minus 4ac is less than 0, then what we get is a complex solution, complex conjugates, as a matter of fact, but complex solution. If b squared minus 4ac is equal to 0, we get a double real root. And if b squared minus 4ac is greater than 0, we get two real roots, two distinct real roots. Okay, so we have this thing that, we realize that in solving this particular type of equation, we run into this b squared minus 4ac, and we see that, oh yeah, that ends up being a very important quantity. Okay, so similarly now with matrix equations, we have something similar, and we call it a determinant. So let's go with a 2 by 2. I want to solve a11, a12, a21, a22 times some xy equals b1, b2. And I know a way to solve this is to find the inverse of this matrix A here. And so if I want to do that, I will use an augmented matrix with the identity here and do my reduced row echelon form work. Now, so if I'm going to have a chance of finding the inverse, I do know that either a11 or a21 needs to be non-zero. So I'm just going to assume that, for now anyway, a11 is non-zero. And so then, if that's the case, I am going to then divide through the top row by that, and I will get 1 in the first spot, then a12 over a11, and then 1 over a11, and 0, and we still have a21, a22, 0, and 1. Okay, so that was the first step. Now I need to take minus A21 times this top row and then add it to the bottom row to zero that part out. So I have 1 A12 over A11, 1 over A11, and 0. And now I do all the algebra. Well, I know, by design I get a 0 here. But now, in this term, I have the A22, and then I'll have a minus A12 times A21 over A11. And similarly here, I'll have the 0 minus, so I'll just get a minus A21 over A11, and 0 times 0 is 0, and then plus 1, I get a 1. Okay, now I need to divide through the bottom row by that number, but it's going to be a lot easier if I get a common denominator first. And so I'm just going to rewrite this with a common denominator. So A12, A11, 1 over A11, 0, 0. Common denominator, I just need to multiply the A22 by A11 over A11. And so I get A11, A22 minus A12, A21, all divided by A11. And didn't do anything here yet. And so we still have those entries. Now I need to go through and make this term here 1. So divide through by that term, this whole row, or multiply by its reciprocal. So I have 1, A12, A11, A11, 0. Now here I have 0 and a 1. Multiplying through by the reciprocal, the A11s cancel, and so I have minus A21 over A11, A22 minus A12, A21. And also then an A11 over that same thing, A11, A22 minus A12, A21. Running out of room. And now I just need to zero out that piece by multiplying the bottom here by a minus A12 over A11, and adding. So I will end up with 1, 0, 0, 1. And now when I well, let me write the bottom in because that won't change. Minus A21. This gets nasty here. A11, A22 minus A12, A21. And then we've got our A11 here. And A11, A22 minus A12, A21. Okay, so in the top, I multiply the bottom here by this minus A12 times the minus A21, and multiply the bottom by A11, and then I need to add that up here. Boy, that's looking nasty, but when I do that, to get a common denominator up here on the 1, I just will need to multiply by this thing down here. So I'll have that thing on the bottom, the A11, A22, minus A12, A21. Okay, so I have that, and then I'll have a plus. This is the nifty part here, is I'll have a plus A12, A21. So those will cancel out when I multiply, this part times this part here. And everything has the A11 on the bottom. And then also this A11, A22 minus A12, A21. And then I'm also left with, on the top here, I need to multiply through by the minus A12. The A11s cancel here and here. And then I'll add all that up there. So I get a minus A12 divided by this whole darn thing again, A11, A22 minus A12, A21. So that's getting old very fast. Now, as you look at this, right, that part becomes 0. That will factor out with the A11 there. And so what I get for all this is I can factor out that thing on the bottom. So I have the denominator is 1 over A11, A21 minus A12, A21. And then times what's left, which is A22 minus A21 minus A12 and A11. And there's the inverse. This is our A inverse. And so what we see is that this will be undefined. This inverse won't exist if, let's see, if my light went off there. So it's kind of, let's see, I guess I'm not being wild enough with my writing. But for A inverse to exist, A11, A22 minus A12, A21 cannot equal 0. And now what you see with this is, let's look back at the matrix that we started with, A11, A12, A21, and A22. And notice I said, well, let's assume A11 is non-zero, A21 could be 0, but if it wasn't, we could just flip them. But notice in this formula here that if A11 is 0 and A21 is 0, we get 0 up in that formula, and so that's a problem. If the top row is 0, we'll get 0 in that. If the bottom row is 0, we'll get 0. If the first column or second column are both zeros, we'll get 0. So that's one thing. If we have too many zeros in there, we will get 0 for this. Now, because of this, right, it determines whether A inverse exists, and so this is the determinant of A for a 2 by 2 matrix is A11, A22 minus A12, A21. Okay, and it's all because if I go to try to make an inverse, I need that to not be 0, and so it determines whether we'll have an inverse or not. Now, we could do the same thing. We can do this, sew this? Well, we could sew it, I suppose. We could do this for 3 by 3, 4 by 4, etc. And you know what happens if I start with a 3 by 3 and I have A11, A12, A13, A21, A22, A23, and A31, A32, and A33. If I go through that same process of finding the inverse, what I find out is that I am going to be dividing by, so I'll have this term 1 over, and I'll have A11 times A22, A33 minus A23, A32. And then I'll get minus A12 times A21, A33 minus A23, A31, and then a plus A13 times what do we have there? 21, A32 minus A22, A31. Okay, that's what I'll end up with, and so we would call this whole thing a determinant for a 3 by 3 matrix. Okay, because that cannot be 0. And what you notice, so if you were to do this sort of brute force, finding these inverses and so forth, you might start noticing this pattern is that in particular, it's very easy to see here and easy to see here. It's a little harder on that middle term. But what you see is we took A11 and then we did the determinant of that submatrix. Okay, that 2 by 2 part of the 3 by 3 matrix, we took A11 times that determinant. Then, for this part down here, we took A13 times that determinant. And for the A12, it's a little bit harder to see, and I'll just kind of X things out, is we took, now in this case, a minus A12, but times the determinant of that, and that. That's submatrix. And so you see, it looks like there might be a nifty pattern, and there is indeed. And so what we'll do is we'll set up some formulaic things, as to how to calculate inverses. But we can kind of get an idea here that, or inverses, determinants, sorry. We'll calculate determinants, but we see that inklings anyway here, some hints that it's going to be a recursive formula. Okay, so determinants are really very nasty formulas in general. But we'll also find ways to simplify finding determinants. So let's just finish with, if I want the determinant of A, another thing I can write is single lines like that. In particular, if I write, A11, A21, A12, A21 and A22 with these straight lines. Notice nothing, it's not a bracket. They look like absolute value lines. So let me get rid of that and make a straight line. When you see that, we're talking about a determinant. And it is just that expression, like a discriminant for quadratic equations. we can look at this determinant and determine then whether A has an inverse or not, right? So there we go. That is what these determinants are all about, and we will go from there.